In the previous video, we saw how orbital diagrams and electron configurations are actually different representations of the already familiar periodic table. In this video, we see how the periodic table can be used as the best guide to writing the electron configuration of any element. Now, we've already seen how the S, P, D and F blocks of the periodic table correspond exactly to the subshell designations in orbital diagrams and electron configurations, and we can even break these blocks up into subblocks, if you like, corresponding to individual subshells, the 1s, 2s, 3s, 4s subshells, etc. And also the 2p, 3p, 4p subshells, the 3d, 4d, 5d subshells, and finally the 4f and 5f subshells. So if the periodic table is actually a different representation of orbital diagrams and electron configurations, then maybe the periodic table is therefore the best guide to both successively filling subshells and to writing electron configurations. So let's use the periodic table to write the electron configuration of lead, which has an atomic number of 82 and therefore has 82 electrons in the neutral atom. Now, lead sits at the bottom right part of the periodic table. It's a metal in the P block, which means it has P subshell filling in the highest occupied orbital, and it's in period 6 and group 14, or group 4a. Now, to write the electron configuration for lead, we first locate its position in the periodic table, as we've already done, down here in period 6 and group 14. And what we're going to do is we start at the top left of the periodic table with element number 1, hydrogen. And we're going to traverse across the periodic table until left to right until we get down to lead at number 82. So we'll go across from left to right. There's element number 1, hydrogen, has a 1s1 electron configuration. We go across this side till we meet helium, and helium has the electron configuration of 1s2. So when we get to the end of period 1, we can write down that electron configuration 1s2. We then come down to the second period, starting with the S block on the left-hand side, and we can traverse these two elements here, representing the 2 electrons filling the 2s subshell, go across to here. These 6 elements here representing the 6 electrons filling the 2p subshell. So when we get to the end of period 2, we can write down 2s2, 2p6. So the next period we'll be traversing across is period 3, and we can see that we're going to go across to 3s2, across to this side of the periodic table, 3p6. Period 4 will be 4s2 here, and this is where we come to the first of the elements in the D block. We traverse across here, 3d10, and there are 10 elements in that D block. And we continue going left to right for those 6 elements in the P block, 4p6. So we got the electron configuration representing those elements in period 4, 4s2, 3d10, 4p6. We do the same for period 5, 5s2, 4d10, 5p6. Period 6, 6s2. So as we traverse across period 6, we encounter the first of the F subshells that fill, because when we hit this part of the periodic table here, we know that elements 57 through to 70 effectively squeeze in here, and so we need to move down to the 4F block, and these 14 elements here need to be considered. So 6s2, 4f14, before coming back to the 5d subshell filling there. So when we get to this part of the periodic table, we're at element number 80, and we've only got these 2 elements here to go to get to element number 82. So the electron configuration corresponding to traversing across period 6 is 6s2, 4f14, 5d10, and 6p2 is when we hit lead at number 82. So the electron configuration for lead is just obtained by combining all of these together. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, and 6p2. And of course, we know we can write a condensed version of that electron configuration by locating the noble gas immediately preceding lead on the periodic table, and that is xenon over here on the right hand side. So we can write down the xenon core. We put the xenon in square brackets, and then all of the remaining electrons. So the xenon core, then 6s2, 4f14, 5d10, 6p2, and those outer electrons representing the electrons corresponding to period 6. So there you have it. If we've been able to write down the electron configuration for lead at number 82, we can write down the electron configuration for any element in the periodic table using the same approach.